Chapter 11 Thermal Properties of Matter.
This video is brought to you by Ace with Dennis. Now, learning can be smart, not hard. Don't forget to subscribe and press the bell notification button to stop missing out free lessons from me.
Internal energy. All matters have internal energy. Internal energy is responsible for the temperature and the state of the matter. Internal energy comprises of the potential energy and the kinetic energy of the molecules in the object. Total molecular potential energy is related to the intermolecular forces and the distance between molecules. Molecules with more potential energy are further apart from one another. Total molecular kinetic energy is due to the vibration of the molecules and is related directly to the temperature of an object. The higher the temperature of an object, the greater its total molecular kinetic energy. Hence, look at this diagram to summarize everything. Internal energy has potential energy and kinetic energy. Potential energy is responsible for the states of the matter, which are solid, liquid, or gas. For kinetic energy, it is responsible for the temperature of the object. Now, let's look at the heating curve of water. We start at negative 20 degrees Celsius. When the water is heated, the temperature increases until it reaches 0 degrees Celsius. At this stage, it is in solid state, which is ice. Since the temperature increases, the kinetic energy increases, and the potential energy constant. When it reaches 0 degrees Celsius, the temperature remains constant for a period of time. And at this stage, the water is in solid and liquid state. It is in the melting process. Since the temperature is constant, the potential energy increases and the kinetic energy is constant. Once we finish the melting process and we continue to heat the water, we can see that the temperature continues to rise until it reaches 100 degrees Celsius. And at this stage, the water is in liquid state. Since the temperature increases, the kinetic energy increases, and the potential energy constant. After you reach 100 degrees Celsius, we can observe that the temperature is constant for a period of time. And at this stage, the water is in a mixture of liquid and gas states, and it is under boiling process. Since the temperature is constant and the water is changing its state, the potential energy increases and the kinetic energy is constant. After the boiling process completes, we can observe that the water starts to increase the temperature again, and it is in the gas state, which is steam. Since the temperature increases, the kinetic energy increases, and the potential energy is constant. Now, let's look at the cooling curve of water. It has the similar concept with heating curve of water. We start at the temperature at 120 degrees Celsius. So we let it cool down, hence the temperature decreases up to 100 degrees Celsius. At this stage, it is in gas state. Since the temperature decreases, therefore kinetic energy decreases and there is no change of state, then the potential energy is constant. Once it reaches 100 degrees Celsius, we can see that the temperature remains constant at a period of time. And at this stage, the water is in gas and liquid state. So it is under condensation process. Since the temperature is constant and there is a change of state, the potential energy decreases and the kinetic energy is constant. Once the condensation process has finished, then we can observe that the temperature starts to decrease again until it reaches 0 degrees Celsius. At this stage, the water is in liquid state. And since there is a decrease in temperature and there is no change in state, we can observe that kinetic energy decreases while the potential energy is constant. When it reaches 0 degrees Celsius, again we observe that the temperature remains constant for a period of time. At this stage, the water is in a mixture of liquid and solid state, and it is under freezing process. At this stage, there is a change in the state of the water and the temperature remains constant. Therefore, potential energy decreases while kinetic energy is constant. Once the freezing process has completed, we can observe that the temperature starts to decrease again. And at this stage, the water is in solid state, which is ice. Since the temperature decreases and there is no change in the state, we can say that the kinetic energy decreases while the potential energy is constant. Specific heat capacity. When an object is heated up, the object absorbs thermal energy and its internal energy increases. If it is not changing its state, there is not melting or boiling, the temperature will increase. The heat capacity, capital C, of a substance is defined as the amount of thermal energy Q needed to raise the temperature theta by 1 Kelvin or 1 degree Celsius. Therefore, the formula is capital C equals Q over the change of temperature delta theta. Or, more commonly, we will use the formula Q equals capital C delta theta, where capital C is heat capacity in the unit of joules per Kelvin or joules per degree Celsius. Q is the amount of thermal energy in joules, and delta theta is the change in temperature in K or in degrees Celsius. Specific heat capacity. The specific heat capacity, small letter c, of a substance is defined as the amount of thermal energy Q needed to raise the temperature theta of 1 kilograms of mass M of the substance by 1 Kelvin or 1 degree Celsius. From this definition, we can get the formula small letter c equals Q over M delta theta, or more commonly, Q equals mc delta theta, where C is the specific heat capacity in unit joules per kg per Kelvin or joules per kg per degree Celsius. Q is the amount of thermal energy in joules, and M is the mass of the substance in kg. Delta theta is the change in temperature in Kelvin or degree Celsius. The larger the amount of heat capacity or specific heat capacity, the more energy is needed to increase the temperature of the substance. Hence, a good thermal conductor will have low heat capacity or specific heat capacity. On the other hand, a good thermal insulator will have high heat capacity or specific heat capacity. Let's look at one example. A glass of water with the volume of 300 cm3 at 80 degrees Celsius is left in a room temperature of 25 degrees Celsius. Calculate the energy lost by the water when its temperature reaches room temperature. Given that the density of water is 1000 kilograms per meter cube, specific heat capacity of water is 4200 joules per kg per degree Celsius. You can pause the video and try to answer the question. Now, let's look at the solution. We know that the formula is Q equals mc delta theta and rho equals to m over v. The mass is rho v. Therefore, from here, Q equals to rho v c delta theta. Then we just substitute the value, and at the end we will get the Q is 69,300 joules. Now let's discuss about specific latent heat. When an object is changing its state from solid to liquid, which is melting, heat is absorbed and its total molecular potential energy increases. The thermal energy gained is used to overcome the intermolecular forces of attraction between particles and hence the particles can move freely. Similarly, when an object is changing its state from liquid to gas, which is in boiling process, it gains more total molecular potential energy. The thermal energy gained is used to overcome more intermolecular forces of attraction and hence the particles are further apart with each other. During the change of state, heat absorbed is not used to increase the total molecular kinetic energy. Hence, the temperature of the object does not change. Latent heat of fusion is the amount of thermal energy needed to change the state of a substance from solid to liquid without changing its temperature. Specific latent heat of fusion, LF, is the amount of thermal energy needed to change the state of one unit mass of a substance from solid to liquid without changing its temperature. Therefore, we can have the formula LF equals Q over M, or we make Q the subject becomes Q equals mLF, where LF is specific latent heat of fusion in joules per kg, and Q is the amount of thermal energy in joules. M is the mass of the substance in kg. So this is the formula that you need to memorize. Latent heat of vaporization is the amount of thermal energy needed to change the state of a substance from liquid to gas without changing its temperature. Specific latent heat of vaporization, LV, is the amount of thermal energy needed to change the state of one unit mass of a substance from liquid to gas without changing its temperature. Therefore, we can have the formula LV equals Q over M. When we make Q the subject, it becomes Q equals to mLV, where LV is the specific latent heat of vaporization in joules per kg, and Q is the amount of thermal energy in joules, M is the mass of the substance in kg. You need to memorize this formula. Now, let's discuss the difference between evaporation and boiling. Evaporation is a process where molecules at the surface of the liquid gain enough energy to overcome intermolecular attractive forces and escape into surrounding. Let's look at the diagram to illustrate the process. We have a water molecule. One molecule of liquid approaches the surface and the molecule returns back to the liquid when it does not have enough energy to overcome attractive forces from neighboring molecules. If it has enough energy to overcome the attractive forces, it will escape from the surface, bringing away some thermal energy. This gives cooling effect on the surface. Evaporation and boiling are different processes, but they have one thing in common, which is the change of state from liquid to gas. Now let's compare the difference between boiling and evaporation. Temperature. Boiling only happens at a fixed temperature, which is called boiling point. For evaporation, it happens at all temperature, including boiling point. Speed. Boiling is a quick process. Evaporation is a slow process. Place of happening. Boiling happens throughout the liquid. Evaporation happens at the surface of the liquid only. Heat direction. Boiling, substance absorbs heat from a heat source. For evaporation, substance loses heat to the surrounding. Cooling effect examples. When sweat evaporates on our skin, it draws away the heat from our skin. Therefore, we feel cool. We feel cold when we hold a metal door knob because the doorknob draws away heat from our hand. Dogs salivate to cool themselves down. Rabbits have long ears and elephants have large ears to act as cooling fins and fans. Now, let's discuss some factors affecting the rate of evaporation. The first is temperature. The molecules of a liquid with higher temperature move at higher speed and have sufficient energy to escape from the surface. Hence, the liquid evaporates faster. A liquid will also evaporate faster at surrounding with higher temperature. The warmer the surrounding, the more heat is supplied and absorbed by the molecules of the liquid. Second, boiling point of a liquid. Liquids with lower boiling point will evaporate faster. Third, exposed surface area of the liquid. Larger exposed surface area provides more space for molecules to escape. Hence, evaporation is faster. Next, humidity of the surrounding air. When the surrounding air is humid, there is high concentration of water vapor in the air. This slows down the evaporation rate. Air pressure. Air molecules exert pressure on the surface of the liquid. Hence, high air pressure slows down evaporation rate. Movement of air on the surface of the liquid. Wind prevents the building up of a layer of vapor molecules at the surface of the liquid. Hence, it increases evaporation rate.
That's all for this video. Thanks for watching. Do you have any question or doubts to ask? Feel free to write down in the comments. I would love to hear from you. Do you like this video? Please don't forget to like it and share it. Alternatively, you can also enroll this full revision course at Udemy. At Udemy, you can track your learning more effectively. Download my notes in printable PDF form. Take a summative quiz at the end of each chapter. Get your first-hand updated contents from me. Get quicker response from me, and many more. You can get all these benefits at a very affordable price. It is one-time payment, no recurring fees, no hidden costs. This saves you thousands of dollars on expensive tuition fees and revision crash courses. And most importantly, your precious time. Finally, you can do your revision anytime you like, anywhere you prefer. All is available within your fingertips. Check out the description below this video and click on the enrollment link to register the course at discounted price. Alright, until then, see you in the next video. Have a great day ahead.